Welcome to another video. In this session, we want to solve a question under Abelian group. This is abstract algebra. So an Abelian group is the frame of reference. So this is the question. Let the set G is equal to alpha 1, alpha 2, and alpha 3. This is a set where alpha 1 is equal to minus half plus I over 2 root 3. Alpha 2 is equal to minus half minus I over 2 root 3. Alpha 3 is equal to 1. They now want us to investigate that is G, multiplication and Abelian group under usual multiplication. So in order to investigate this, it is pertinent and also germane to show some properties. So before I solve this question, I'd like to tell us what an Abelian group is. And how do we define an Abelian group? I'm going to define it using the properties of closure, properties of associativity, properties of identity, properties of inverse, then properties of commutativity. So once those 5 properties are satisfied, hence the group is Abelian. So what are we saying? That if we want to define a group, let G be a non-empty set endowed with a binary operation star. The couple G, star is said to be a groupoid if for all A, B in G, A asterisk B is in G. So if that one is satisfied, the group is closed. Then secondly, let G be a non-empty set endowed with a binary operation star. The couple G, star is said to be a semigroup if for all A, B in G, A asterisk B is in G. That is property 1. Then property 2, for all A, B in G, there exists another element C in G such that A star B in brackets star C is equal to A star, then open bracket, B star C. So that is associative property. Once associative property is satisfied, that group is a semigroup. Then the third one, that is identity property. And when it satisfies the identity property coupled with associativity and closure, that group is called a monoid. So when you are having an identity for all A, B in G, there exists an element E in G. That E is an identity element such that A star E is equal to E star A is equal to A. So if that property is satisfied, the binary operation coupled together with the set is called a monoid. Now, how do we know that it's a group? Now, if we add the property of inverse to the property of monoid, we can now say a group is a monoid that has an inverse. So if the property of inverse is satisfied, then it's called a group. Now, in order for us to call it Abelian, all the 4 properties above, if the property of commutativity is added, that means for all A, B in G, A asterisk B is equal to B asterisk A. So if all those 5 properties are satisfied, it is called a group. It is called an Abelian group. Now, with reference to this question, we are going to perform an operation table. Solution. We are going to perform an operation table using the properties I stated. So this is how our operation table will look like. We are going to have the vertical and horizontal column. So this is alpha 1, alpha 2, alpha 3. Then the operation is multiplication. Then on this vertical column, we have alpha 1 as well, alpha 2, alpha 3, because what is in the set are alpha 1, alpha 2, alpha 3. So we are going to place it like that. So how do we now get the result? We are having 1, 2, 3, 4, 5, 6, 7, 8, 9. We need to fill in this gap. So by performing this operation, so let's say alpha 1 is equal to, now from the context, our alpha 1 is equal to minus half plus I over 2 root 3, then multiplied by alpha 1. We are multiplying it by itself. Minus half plus I over 2 root 3. Now let's do that. Let's do the multiplication. So alpha 1 is equal to half minus half times minus half is 1 over 4. Then minus half times I over 2 root 3 will be equal to minus I over 4 root 3. Plus I over 2 root 3 multiplied by minus half, that will give us minus I over 4 root 3. Just the normal expansion. Then the last one, I over 2 root 3 multiplied by I over 2 root 3. So I have plus I squared over 4, because 2 times 2 is 4. Then root 3 times root 3 is 3. So note, I squared is equal to minus 1. I squared is equal to minus 1 because I is an imaginary number. We also call it a complex number because I is equal to the square root of minus 1. So when you square the square root of minus 1, the result is minus 1. It's minus 1. So that implies that I square is equal to minus 1. So anywhere we see I square, we are going to be replacing it with minus 1 because it's an imaginary number. So we can now say from here that we collect the like terms. Then 1 over 4. Then this and this are alike. Minus I over 4 root 3 minus I over 4 root 3 will give us minus I over 2 root 3. That is the addition. Then I said earlier on that I squared is equal to minus 1. Minus 1 times 3 is minus 3. That gives minus 3 over 4. So when you couple these results, when you collect the like time, this is an imaginary number, we leave it behind. We collect the like times. 1 over 4 minus 3 over 4 will give us minus half. So that means the result of this will give us minus half minus I over 2 root 3. So minus half minus I over 2 root 3 is the result. So check the result here. Minus half minus I over 2 root 3. So which gives us alpha 2. Because this result is the same as what is in alpha. So alpha 1 is alpha 2. So let's find alpha 2 as well. So alpha 2 is equal to minus 1 over 2 minus I over 2 root 3. So they are the same. Then alpha 2, the same thing, minus half minus I over 2 root 3. So let's do the expansion. Minus half times minus half is 1 over 4. Minus half times this is equal to plus I over 4 root 3. Minus I over 2 root 3 multiplied by minus half. That is plus I over 4 root 3. Then the last one, this expression multiplied by this expression will give us minus times minus is what? Plus. I times I is what? I squared. 2 times 2 at the denominator is 4. Then root 3 times root 3 is 3. And so we have, let's collect the like terms. We will discover that we are having this as 1 over 4 plus, now these ones are alike. I over 4 root 3 plus I over 4 root 3 will be I over 2 root 3. Then I square, as I said earlier on, is minus 1. So minus 1 times 3 is minus 3. That is minus 3 over 4. So let's check again. This multiplied by this is I squared over 4. So that is plus I squared over 4. So root 3 times root 3 is 3. So this coupled with this, you are having I over 2 root 3 plus, that is minus I squared is minus 1 over 4. So that is minus 1 over 4 multiplied by that is minus 3 over 4. So the result of this, 1 over 4 minus 3 over 4 is minus 1 over 2, then plus I over 2 root 3. Now let's check for this result here. So we need to be very careful because of the imaginary numbers. So that is why I'm taking my time to check, so that there will be no error. So this is minus half plus I over 2 root 3. So that is what? That is, so we are multiplying alpha 2, alpha 2. So an alpha 2 gives this result, which is minus 1 over 2 plus I over 2 root 3. So the result here is alpha 1. So alpha 2, this result is alpha 1. So alpha 2 multiplied by alpha 2 is alpha 1. Then the last one, alpha 3 is equal to, now that means we are multiplying, our alpha 3 here is 1. So alpha 3 is 1 times 1. So in the operation table, so we are having 1. So, and 1 is same thing as what? Alpha 3. So when you multiply alpha 3 by itself, it gives you alpha 3. So the next thing is now to complete other part of the table. So we are multiplying alpha 1 by alpha 2 now. Alpha 1, alpha 2. Alpha 1, alpha 2 is equal to now minus 1 over 2 plus I over 2 root 3. Then multiply by alpha 2 is minus half minus I over 2 root 3. So let's do the expansion. So this is just like a conjugate expression. So let's do it. So if you want to perform this is a conjugate expression. Recall that if you are having x plus y multiplied by x minus y, if this is x, this is y. This is x, this is y. So that is x plus y, then bracket x minus y. So that is a, so when you do this properly, you have difference of 2 squared. So the result of this should be x squared minus y squared. So instead of me going through this rigorous process, I will just shortcut it since it's conjugate. I will just say minus half all squared minus, this is my x, y, this is my y. Then minus I over 2 root 3 all squared. So minus 1 over 2 squared will definitely give us 1 over 4. So I raised to power 2 is I squared, and I squared is minus 1. So that is minus 1. So this minus into minus 1, then square of 2 is what? That is 4. Square of root 3 is 3. So let's put them together. I'm having 1 over 4. Minus coincide with minus, it becomes plus. Multiply by 3, that is plus 3 over 4. So that implies that alpha 1 over 4 plus 3 over 4 is equal to 1. And when you look at 1 here, 1 is equal to alpha 3. So that is alpha 3. So that implies that alpha 1, alpha 2 is equal to alpha 3. Then alpha 1 times alpha 3. Since we know that alpha 1 is this expression and alpha 3 is unity, is 1. 1 multiplied by anything, nothing will change. So alpha 1, alpha 3 will now be same as what? Alpha 1. So alpha 2, alpha 1 is equal to, because we knew that alpha 1, alpha 2 is alpha 3, so nothing is changing. Alpha 2, alpha 1 is also alpha 3. Then alpha 2, alpha 3. We said earlier on that alpha 3 is 1. So 1 times alpha 2 is alpha 2. So nothing has changed because 1 multiplied by alpha 2 will remain alpha 2. Then let's complete this. Alpha 3, alpha 1. Alpha 3 is 1. 1 times alpha 1, nothing will change. Then alpha 3 is 1. Alpha 3 times alpha 2 is also alpha 2. We successfully completed the operation table. Now, here we go. Now, the question now says, is G, multiplication and abelian under usual multiplication? So that is what is left for us to prove. So now, let's start from the property of closure. Since every element in the operation table belongs to G, that is the set. Hence, G, multiplication is a groupoid. So when I say it is a groupoid, what does that imply? That is, operation multiplication is closed. So when it's groupoid, that means it is closed. So that is property 1. Because we are going to find properties in order for us to say that the group is abelian. Then property 2, we want to check for associativity. So associativity, we are going to involve 3 elements of the set in accordance with the binary operation, which is multiplication. So for all alpha 1, alpha 2 belonging to what? To set G, there exists alpha 3 belonging to set G such that alpha 1 cross alpha 2 alpha 3 is equal to alpha 1 cross alpha 2 multiplied by alpha 3. So we want to check for associativity. We check whether the left is equal to the right. So let's do that. So alpha 1 multiplied by that alpha 2, alpha 3 in the operation table, alpha 2 cross alpha 3 is equal to alpha 2. So alpha 1 cross alpha 2 on the left, because this result is alpha 2, then is equal to alpha 1, alpha 2 in the operation table is equal to alpha 3. So alpha 3 cross alpha 3. So what we're having on the left is alpha 1, alpha 2, and alpha 1, alpha 2 is alpha 3, which is equal to alpha 3 is also alpha 3. So that means since alpha 3 is here, alpha 3 is here, it is associative. It is a semigroup. It is a semigroup. That is the second property. So that is the property of associativity. Then 3. We need to prove for the property of identity. Now it is crystal clear from the operation table that the identity element is alpha 3, because I know that when you operate alpha 3 with any of alpha 1 and alpha 2, nothing has changed, because alpha 1, alpha 3 is alpha 1, alpha 2, alpha 3 is alpha 1, alpha 3 multiplied by itself is also alpha 3. So from the operation table, it is clear from the operation table, it is clear that the identity element is alpha 3, because when alpha 3 is operated on alpha 1, alpha 2, and alpha 3, nothing has changed. So hence, the identity property is satisfied. So that means if the identity property is satisfied, we can call it a monoid. This is a monoid. Now the fourth property is to check whether it's a group. So how do we know whether it's a group? We need to check for the property of inverse. Now when we say inverse is what you operate on the existing element of a set, that the result gives you identity. We now go back to the operation table. Now we can see that when we operate inverse on a certain element of a set, the result must be, I do now check for the result that gives identity. Now, in this operation table, when alpha 1 is operated on alpha 2, the result is identical. It's clear that our identity element is alpha 3. So alpha 1, alpha 2 is alpha 3. Alpha 2, alpha 1 is alpha 3. Alpha 3 is alpha 3. So what we are trying to do here is that any element you operate on another element and the result is the identity, definitely that second element will be the inverse of the first element. So alpha 1, alpha 2 is the inverse of alpha 1. Similarly, alpha 1 is the inverse of alpha 2. Alpha 3 is the inverse of itself. So hence, inverse property is satisfied. Now, the last stage is to check whether it is commutative. So how do we check that it is commutative? A commutative group is also an abelian group. Once I check for the property of commutativity, then the group is abelian. So the fifth property, for all alpha 1 belonging to set G, there exists alpha 2 belonging to set G such that alpha 1, alpha 2 is equal to alpha 2, alpha 1. Now let's investigate from the operation table. Alpha 1, alpha 2 is equal to alpha 3. Alpha 3. Then is equal to, then alpha 2 multiplied by alpha 1 is also equal to alpha 3. So you can now see that the group is commutative. Hence, the group is commutative. So since the group is commutative, so hence the group, or I say hence G, comma multiplication, let me put it that way, G comma multiplication is indeed an abelian group. So that comes to the end of the session. So don't forget to subscribe to my YouTube channel. So life is continuous, life is differentiable, life is integrable, but not the best measurable. It is a diet.